Well, first of all, a big thank you to all you guys. I know I bullied everybody a little bit by email today to get people to come out. I think you're in for a real treat. This was meant to be one of the George and Maureen Ewan Lecture series events. Unfortunately, because of the weather, George Ewan himself couldn't be here. It's an event that we hold a couple of times a year where we bring in a very distinguished guest to talk about physics and to talk to the public and to talk at a level that I think you'll get a lot out of the talk this evening. So George was in particular keen to bring people in that would spend some time in the department. So I'm extremely happy that our speaker tonight spent yesterday and today interacting with the students, interacting on panels, and being a participant in our department. And so I'm not going to go on. I know that I promised you, at least those who are in APSC 112, I guess you had an exam last night. Good, bad? Good. An exam tomorrow, right? And so this will be great handy for you, a nice opportunity to sit back, relax, hear about some really exciting physics. So I'm going to ask Aaron Vincent actually to introduce our speaker. Aaron is a professor here in the physics department. Has some affiliation himself with the IceCube collaboration. The IceCube is one of the research areas of the department. And so if you hear things that you like, you might want to be approaching some of the faculty members associated with IceCube about possible work on various projects.
Thanks, Tony. Yeah, so for my astronomy students that are here, most of this is not on the exam. Only one or two of these slides. Yeah, so it's a really, it's a pleasure to introduce Francis Halzen, who's our speaker for tonight. So Francis originally hails from Belgium. He grew up there. So he did his PhD and undergraduate degree and PhD at the University of DUMAND before being convinced to move to Madison, Wisconsin, of all places, in 1971, and I hear he hasn't looked back. So Madison was, for a long time, the center of particle phenomenology in the US, and is now arguably the center for astroparticle theory, or astroparticle physics in the United States. So I would call it America's Kingston. So Francis has many titles and roles. I'll just give you a few just to give you a flavor. So he's been the Robness Faculty Fellow, the Gregory Bright Distinguished Professor. In 1991, he was named the Hilldale Professor. He's been nominated as a Fellow of the American Physical Society. He has honorary doctorates from Uppsala University, from Ghent, from the Southern Methodist University. He has a geographical feature in Antarctica named after him, the Halzen Mesa. He was voted top chef 3 years in a row in the United States. That's not true. He's won the European Physical Society Piccioni Prize, the Smithsonian American Ingenuity Prize. There's a book that's recently been written called The Telescope in the Ice that mostly follows Francis around and has great anecdotes and a lot of dirt if you'd like to learn a few interesting things about not just Francis Halzen, but also the history of the neutrino and the telescope that we're going to hear about today. More relevantly, so he started his life as a theoretical particle physicist and is now the PI and his co-spokesperson, has been for the past 15 years or so. The IceCube Neutrino Observatory, arguably the largest scientific experiment, maybe by volume, in the world. So that shows that there's hope for us theorists. He has hundreds of papers, tens of thousands of citations, but more importantly, it's always a pleasure to talk to him and to hear what he has to say. I think he's going to tell us some very interesting things about looking for neutrinos in Antarctica. Okay.
Cannot possibly live up to the expectations. I'm going to talk about the IceCube project, and I always start with this slide because I know you had an exam yesterday and tomorrow, but if you came for entertainment to see pictures of penguins, you're in the wrong place. saga of this experiment happens in this place. This is a picture of the geographic South Pole. So it's the bottom of the Earth, not Antarctica, the very middle of it, the geographic South Pole, and it's a desert. There are no animals, there is no vegetation, there's nothing. So what brings us there? Two things. If you stand here on top of 3 kilometers of ice, there's an ice sheet that's 3 kilometers deep, and that's what we were interested in. And so I cannot show you the eyes of the detector, but if you would imagine a new globe where, in fact, the South Pole is on a glacier that runs off from the West Antarctic mountain range, runs eventually in the Indian Ocean. So you can imagine a sheet of ice like 3 kilometers in size, and we are going to build a particle detector in the middle. Not that we were clever, but we were incredibly lucky. We had no clue, actually, whether we would find clear ice to build a particle detector. To build this particle detector and many other particle detectors, like at CERN or Fermilab, you need very clear material, very transparent, as you will see why later. And we found actually out that the deep ice in Antarctica was clearer than any substance on Earth, whether it's a solid or a liquid. You cannot purify water to match the optical transparency of this ice. And that we didn't know, but you know, it's better to be lucky than smart. And so why is this? Now we know. It's because, like in the middle of the detector, this is snow that fell on Antarctica 60,000 years ago and compacted, and it's ultra pure. And the purity determines the transparency. And in fact, you can purify water to become almost as clear as our ice. That's one reason we are at the South Pole. The other reason is this. There is actually a research station. In fact, this dot here is the geographical South Pole. It moves 10 meters every year, and because it's a glacier, the whole experiment is moving with a glacier. That's this research station that can house, it's like a Holiday Inn for 200 people. That has also, you know, bulldozers and cranes and equipment to build an experiment. This is IceCube, and this is the runway where the planes land. Everything you do there, up to recently, has to go in and fit through the cargo door of a C-130 airplane. And so I promised you no beautiful pictures, but okay, just one in the talk. This is the South Pole Station, and under the Aurora. And the important thing is, this is one of the few places in Antarctica that's open all year round. And so that makes this experiment possible. Now, at this point, I have to tell you everything I'm going to have to explain to you to come to my point, hopefully in less than 1 hour. And that is a long list. I have to explain what a neutrino is, what the cosmic rays are, what neutrino astronomy is. Then I'll finally come to what IceCube is, and then I'll start discussing the results. So what's a neutrino? I think in Kingston you should know by now what a neutrino is, but just in case. You know, you are told in high school that the world is made of 3 particles, the practical world, and the electron, the proton and the neutron form nuclei, and then you put electrons around it, and then you make atoms, and that's the real world. Well, if that's what you learned, you didn't get your money's worth. And that people began to figure out in the early 1930s. By then they knew there was a neutron, a proton, and an electron, and they observed that the neutron actually can suddenly disappear and become a proton and an electron. And as you all know, I hope, if I am a neutron and the proton goes that way, the electron has to go that way. It's classical physics, billiard ball physics. And they noticed that occasionally the proton and the electron would go both in that direction. In fact, they would go in all possible directions. And you could do one thing, you could give up physics, the law, one of the most basic laws of physics. Or you could do the following. You could say, well, there is actually a third particle. If the proton and the electron go in one direction, then there's a particle that I don't detect that goes in the opposite direction. And that's the neutrino. And in fact, Ellis and Mott, if you read this paper in 1933, they totally defined that particle. And by today's standards, this would be the discovery of the neutrino. This is the discovery of the neutrino. It's called the missing mass, missing energy experiment. That's how we detect particles at the Large Hadron Collider in Geneva. Well, they couldn't imagine, remember only 3 particles were known. They couldn't imagine that on the basis of this measurement they could claim another particle. They didn't, but there was some brave theorist who did. And he actually not only realized you couldn't detect that particle, he actually thought you could never detect it. But so, I always used to joke when we were building IceCube, which was, I said we're going to prove him right. Nobody laughed. So that's the answer. That's what the real world is made of. And the neutrino, I mean, does the neutrino fit in this? Well, without the neutrino, you have already understood there would be no nuclear physics. A neutron changing into a proton, that's nuclear physics. And without nuclear physics, well, we wouldn't be here for many reasons. The Big Bang produced neutrinos. When stars explode, they explode because of neutrinos. And stuff that stars are made of is what we are made of. The sun wouldn't shine without neutrinos. I think you know that in Kingston. And so we can go on and on. You emit neutrinos from the salt decaying in your body. And this is important. You recognize, look at this picture carefully. You know, when this is a nuclear, my plane got cancelled, I think. So when you see pictures of nuclear reactors, they're always sitting in water, which is a good idea to shield the radiation, and that water is always blue. Remember that. That's an important thing in this talk. And another important thing is that if you look up at the sky, neutrinos reach the Earth literally all the time. In fact, IceCube, as I stand here, this detects neutrinos every few minutes. It detects a neutrino. But they are neutrinos produced by cosmic rays interacting in the atmosphere. So cosmic rays are protons, and they are produced somewhere in the universe. We don't know where, except I'll change that at the end of this lecture a little bit. And the protons hit the atmosphere, interact with nitrogen and oxygen, and produce particles called pions that decay into muons and neutrinos. And those neutrinos are interesting for other reasons, but they are really annoying because it means if you want to see the universe, you have to look through the atmosphere. And the atmosphere glows in neutrinos. And it's not like clouds to astronomers. These clouds never go away. And so that's quite a challenge. So I'm now introducing the subject of astronomy. And so you have by now decided that you may not want to use neutrinos to do astronomy, That's what clever people decided. But so why do you want to do this? Well, this is my version of astronomy in 4 slides. Astronomers have been very successful at changing the color, the wavelength of the light, or the energy of the photon, depending, this quantum world. This is a picture of the universe in visible light. And I just showed this also. This is our own galaxy. This is the galactic plane. When I show pictures like this, it shows the universe, but the center, the major axis is of the ellipse, are the sources that are in our own Milky Way. Now, that's the sky you see above Kingston, and if you turn to extreme red light, then the sky looks like this. Has nothing to do with the previous picture. This is the sky at 10 to the -4 electron volts, or wavelength of a fraction of a millimeter. This is the microwave background, which will also play a role in this talk. There are 411 microwave photons in the universe in every cubic centimeter in this room. So you cannot think of the universe as an empty place. It's filled with this stuff. And then, instead of going from visible to red, I can go from visible to blue, and then the sky looks like this. And these are photons. These are light particles of light with about 1 GeV energy. And you can play this game with all the wavelengths and energies of photons in between, and this has been very successful. And so you can extend the radio waves on one side, and you would like to extend this to the other side. So you build an instrument that sees, say, the universe at much higher energy than this, and that's what you see. You see absolutely nothing. This game doesn't work anymore. You cannot keep making the light bluer and bluer. At some point the universe turns black. And the reason is very simple. If you have you have some far away, some object that produces light. That light doesn't get through the Earth. That particle of light will somewhere meet one of these 411 per cubic centimeter and produce an electron-positron pair. And once you have charged particles, astronomy is finished. You cannot do astronomy with charged particles. I told you earlier that protons reach us from the universe. And we don't know where they come from. And the reason is that they are bent in magnetic fields of the Earth, magnetic fields in our galaxy, magnetic fields outside our galaxy. And so you can produce them there, and you will detect them from here. So the sky is totally scrambled. And so, is this a serious problem? Well, here is another slide of this. You see here the different wavelengths of light here, and so it means about 1/4 of the universe we have never seen. It's like the dark side of the moon. And why isn't it half the universe? Well, it may be. We don't know. But we know we detect cosmic rays with energies that reach to here. So at least this part we missed. And it's about 1/4, 20% or more. And so is this, maybe this is not interesting. Maybe there's nothing to see there. We don't know. So, but if you are a particle physicist, you cannot resist thinking about this problem, because it's not just astronomy. If you think of these highest energy particles that were on the right side of my plot, they have an energy of 100 million TeV. Doesn't matter what a TeV is, tera electron volt, it's a measure of energy, like joules, but different numbers. And So you have to think 1 TeV used to be my favorite unit because that's the energy of the accelerator at Fermilab. So that's the small unit in this talk. So on the right-hand side of this plot, you get energies of protons that are 100 million times larger. You'd say, what about the LHC? Same thing. It's 10 million times larger. And so they must, the universe must be able to produce these to accelerate these particles. And I already told you we don't know where they come from because they are charged. And we have no idea how they're really accelerated. And the only thing we really know since last year is that the highest energy of these particles are extragalactic. The accelerators don't live in our galaxy, they're from outside our galaxy. And we always guessed that, but now we're sure, thanks to the Auger experiment. And most of the cosmic rays are produced inside our galaxy. Many are produced by the sun. But when I say they were discovered in 1912, this is the oldest problem in astronomy. Here we are 107 years later, and we have no clue. And so the fascination of particle physicists, I remember when the news came out that an experiment in Utah saw this event of 3 million TeV. Well, to think about that, if someone gave you LHC magnets, you would have to fill the orbit of Mercury to accelerate that particle. And, I don't think nature does it that way, but, how can you not be obsessed by trying to solve this? And of course, that's where the neutrino comes in. The neutrino has no problem with this. It doesn't interact with anything. So this cosmic accelerator, just like our accelerator at Fermilab, can produce neutrinos. And it was only a guess how many. There was another gamble. So neutrinos overcome all these issues. So it's an ideal cosmic messenger. In fact, you first have to think of neutrino as being exactly like light. It has no electric charge. It has no mass in this talk, I'm sorry. But Art is in Honolulu right now. It shows he's smarter than us. Essentially unabsorbed, and it tracks nuclear processes. You can only produce neutrinos where you produce pions and kaons with accelerators, because the pions and kaons are the ones that then decay in neutrinos. So when we make a map of the sky in neutrinos, you not only see cosmic ray accelerators, you only see cosmic ray accelerators. It gives you exactly what we were looking for. They are difficult to detect, that you will realize during this talk. So, but the real reason to do this is, and I could spend the rest of the talk on this subject, when we went through all these different telescopes looking at light at different wavelengths, there is a general rule. The things you were looking for, they really never found or were not interesting. And you only found something different than why you built a telescope. And what you found, of course, was much more interesting than what you could imagine. And that's why you have the opportunity to do this, you want to do this. You get in trouble with this argument because people think you're taking research money and gambling with it, which is essentially what you're doing. And someone in Washington told me, this is a dangerous slide. I say, what do you suggest? And this is what he suggested. He works, so the idea was, let's build this thing. It cannot be uninteresting. Okay, so now, there was some bad news because theorists like me and many others, more clever, and more distinguished, had for a couple decades counted the number of neutrinos we could expect. And the news was not very good. If you wanted to really have a shot at this, you had to build a kilometer square telescope, which means a kilometer cube neutrino detector. You cannot detect neutrinos with a mirror. And so since 1960, the work, well, a bit later, the work was, yeah, in the late 60s, the work was out, we want to build a kilometer cube neutrino detector. And how to do this, the idea is not new. Goes back to this man, Markov, a Russian physicist. And I will, this is what he wrote in a talk he gave in 1960 in Rochester, New York. But I have a cartoon here of what he suggests. He first suggests that you look for neutrinos coming through the Earth. You know, forget this stuff up there. Because if you detect particles coming through the Earth, they can only be neutrinos. No other particles come through the Earth. So you use the Earth as a filter. Then, of course, a neutrino has no charge. That means it flies to your detector, you don't see it. It doesn't make light in a detector. But if a neutrino interacts, it disappears, makes a small nuclear reaction, it has to interact with the nucleus of your whatever, of the water. And then it disappears, but makes charged particles. And these charged particles can travel through your detector. And they are charged, they excite the atoms, they make light. And if this is a muon neutrino, this is a muon, it's one of these particles. And a muon travels through water for kilometers. And so it travels at close to the speed of light, at the energies we are interested in. But light itself in water doesn't travel, it travels at 3/4 of the speed of light. So the muon outruns the light it makes, so it makes like a speedboat outruns the waves on the water. It makes a shock wave, and so you measure this shock wave, and then you know where all this stuff comes from. So you not only detect a neutrino, you have a telescope. So that was his idea. So you have to think of this as a nuclear reaction, and you can think of all these particles making blue light. Just like that's what you were seeing in the water, covering the reactor. So it's that blue light. We're detecting the blue light from the reaction of one elementary neutrino, one elementary particle. And so how do you detect light? That's the easiest part. You detect light this way. So this looks like a light bulb, but it detects light. It doesn't emit it. So when light hits this object, engineers in Japan managed to build this thing so that a little electric current comes out, and you send that to your computers. And so you detect light. And so this way you try to detect, you fill a kilometer cube with enough of these things that you can efficiently map this direction. So you know all the physics. This is the physics of the light. And again, in case you didn't get it, this is how you see where the neutrino comes from. Even if I didn't see the duck, I would know in which direction it's going. And in this case, I certainly don't see the duck. And now you say, well, water and these big light bulbs that detect light, I've seen that before. And in fact, you did. This is the Super Kamioka detector in Japan. It's in the Japanese Alps. And so it's water, and it detects neutrinos this way. Here is another picture, cannot resist showing. So these are all these light sensors called photomultipliers. And here you see the water being, the detector being filled with water, and they're going to look for neutrinos. So what's wrong with this? This is 10,000 times too small. And it's not small. You know, if you make kind of a circle out of the back wall and then make it as high as wide, that's what this experiment looks like. I've actually hung with my feet from the top and looked at this incredible sight to look at this experiment. So people in Hawaii spent like 15, almost 20 years to try to do this experiment that Markov suggested. And unfortunately they failed. But along the way they discovered a lot of the techniques that we still use. Now, how this got into our brains, I don't know, but what we decided when they failed was that this would be easier if you went to the South Pole and put these glass spheres a mile deep in ice rather than in the ocean. And this sounds hard to believe, but it's true. It's much easier. I'll tell you how. So here, that was the idea. Here you see one of these detectors going, and it will end up 2.5 kilometers deep in the ice. And so we started to try this out, and I was a theoretician, so I had no lab. So I had a place where theorists play table tennis. We removed the table, and with a colleague of mine, Bob Morse, we built these modules with the hope to deploy them in the ice. You can imagine that this was crazy. But it took us about 10 years or more, and we figured out how to do this and build a small experiment that had 700 of these sensors. And this is we finished it by 2000. This is the geographic South Pole in the year 2000. And you see the station is not there yet. And so you see here these photomultipliers and the Amanda lab on top of it. And so we detected neutrinos, and this is what you're looking at. Each of these black dots, of the 700 black dots, is one of these sensors. And when they detect light, they become colored. If they detect a lot of light, you see a big colored dot. And this, a small dot like this, that's one photon detected. And you can, with your eyes, reconstruct the direction of that muon, which is how you do astronomy, to a degree or so. And so what you are looking at is a cone of light traveling through that detector. We detected some 300 of these. Of course, you can imagine they were the ones produced in the atmosphere. Totally uninteresting at the time, not anymore. You know, I'll give you some hint. You face the snow, I have to tell you something useful. If you want to do science and you want money, you publish in Nature and make exaggerated claims. We published this paper in Nature. By then, we had brave people from Germany and Sweden who joined us with no guarantee of success. And we said we now knew we could build a kilometer cube detector. We were declared one of the 7 wonders of astronomy by Scientific American. Here we are, in fact, we were alone in this category. And now you think it would be easy. We had solved the problem how to do this. But people couldn't believe, you know, this is the picture that goes, people could not believe that this was the simplest way to build a kilometer cube neutrino detector. But it was. I mean, they still have not produced a detector like this in the Mediterranean. I think they will, they started. But so the facts have proven that this is the easiest way to do it. So we built a kilometer cube, we filled a kilometer cube of ice, 1.5 kilometers below the surface, with more than 5,000 of these light sensors. So the same as the Amanda experiment, just much bigger. And that's it. And so now I'm going to go back to science, but well, this is science too. How do you put these photomultipliers in the ice, and why is it simple? And it is simple, except much more difficult than we anticipated. So this is actually what we call the hot water drill that deploys this photomultiplier. So I have a 2-minute movie that will tell you the whole story in 2 minutes. So the first 80, 90 meters at the South Pole is snow. So you just melt your way through it. Okay, that's the easy part. Then comes this thing that's called the hot water drill. And it puts out hot water under pressure and melts the ice. And it falls by gravity. And after 2 days, you get a hole that's 2.5 kilometers deep and has transformed ice into water. This takes a 4.8 megawatt heating plant, which is 45 car wash heaters. And so it puts out 200 gallons per minute, close to boiling. So this whole operation is like a circus train, but it's on sleds rather than on wheels. This is the drill tower. This is a marvel, actually, of technology. It's a 2.5 kilometer hose in one stretch that goes right to the depth. These are the car wash heaters, and these are the generators converting fuel to power the car wash heaters. So after 2.5 days, this comes out. You have to realize ice is an insulator, so that water remains liquid for a long time. And we guarantee that it remains liquid like for 30 hours or more before it refreezes. Then the circus moves 125 meters away and does exactly the same thing. But now, at the hole is a misnomer, because there's water in it, there are 60 of these sensors in pressure vessels, and you see this is the cable that powers them and that brings back the signals, and every 17 meters we attach one of these photomultipliers, and then you see this is the last one, and then it sinks to the bottom of the hole, and so below 1.5 meters you have 60 photomultipliers instrumenting 1 kilometer. Then the ice refreezes and you take data. That's it. You do this 86 times, and that's the IceCube experiment. I should say that it was not always that easy. That's not me. You see here, this, if you could go inside the detector, that it would look like. You would see this string with 60 modules. This is 17 meters. It's like the height of this hole, this to here. And if you look 125 meters away, there's another string, etc. So all these strings then come up. This is 20 of them. You can only drill make these holes in December and January. So this was a good season, 20 of these cables deployed. And so these cables then go into this building, and this building is just filled with computers. And what these computers do, I can show the movie, what they do again, here is a muon, one of these muons. It's one that comes from above, unfortunately. You see the light it makes, and then you see how the detector responds to this blue light. And from the information provided by these modules, we can reconstruct everything about this neutrino. So, if you want the flavor of how this works, here is, I'm going to show you IceCube in action. You first have to realize that, you know, we are a mile deep in the ice, but particles from the surface, certainly the neutrinos, but also the muons, constantly hit the detector, and you are not really interested in them. So, from the South Pole, you see these cosmic ray muons, which you wish you didn't. then you see neutrinos produced in the atmosphere everywhere on Earth. And then you are looking for actually a handful of interesting neutrinos. And so this is a movie of the detector taking data. You see all these light signals arrive, right? And then the computers at the surface fit tracks to these objects. You can actually, this movie repeats, and you can see at some point there is a big bundle of muons. There's a very energetic cosmic ray that produces many muons at the same time in the atmosphere, and then send them through your detector. So this movie is 10 milliseconds long. So we actually collect 100 billion muons per year, 100,000 neutrinos, actually more. But this is all background. We are looking for 10 to 100 interesting events. That's how this works. So, in other words, 1 every 6 minutes, it's now more like 1 every 4, and 3,000 of these annoying muons coming from the atmosphere per second. Some people do very interesting physics with this, but that's another talk. Even during construction, we saw events like this that kept us going and that kept us dreaming. You see the color, actually, I didn't tell you that. The color tells you the direction, you follow the rainbow. So this is a neutrino that came through the Earth. And with a bit of practice, you can guess the energy. And this looked like a neutrino that couldn't be produced in the atmosphere. Anyway, you cannot claim such a thing. And so we had 2 years of data and we were getting very nervous. I like to show this slide because unfortunately it's not useful anymore. But you know, when you read New Scientist at the time, and you realize they were betting 6-to-1 odds that we would detect cosmic neutrinos. You could bet on this. This was a real website where you could bet money. And in fact, the Higgs was 6-to-1 also. So you could have made a lot of money. And we actually tried. LIGO detecting gravitational waves was 500-to-1. And we started betting on that. And then they took the webpage down. But I must say I don't think this was funny at the time, even though it says, it compares it to the odds for seeing Elvis alive and the Loch Ness Monster. I didn't think it was funny. But then again, we were lucky. It just happened. You know, when you have a collaboration, once the collaboration by now is maybe 300 people, and once a week, you get all together on the phone and talk to each other and say what you have done the last, you know, it's organized. And this is very boring, you know, you sit there catching up on emails. And I remember the moment someone from Japan showed this event. And you can immediately see this is a neutrino, nothing comes in the detector, it starts in the detector, so it's a particle. In fact, rather than producing a muon going through the detector, this neutrino hit the detector head on. And from the size of the ball, we could immediately tell this is 1000 TeV, this is not produced in the atmosphere. And there it was. We were looking for something else and didn't find anything, but this showed up when we looked at the first 2 years of data. This is not something that you can easily ignore. This is the event superimposed on the data center in Madison. This is the campus. So if you imagine Kingston and take 5 city blocks, that's the size of this event. And so let's see if that's there. No. So you say there is no muon track. Well, there is no muon track. This is an electron neutrino or a tau neutrino, but it doesn't matter. We knew we could see these events too, but weren't looking at the time. So everybody ran off and decided, by now everybody has told, you look for events that just start in your detector and look at their energy. And don't let any light come in, just make sure they all look like that. We went to very complicated analysis, but it didn't matter. We ran to the same 2 years of data and found 26 more events. So you can see, I showed you all of them. And then we published in Science that we thought we had discovered cosmic neutrinos. The next week we were declared the physics breakthrough of the year, and I didn't sleep for several nights. You know, I remember giving this press conference, the only thing that I was thinking of is, what do we say when this happens not to be true? And I still dream about it. We were supposed to do this. So what happened to this? Well, some graduate student was sitting in an office in Madison. Nobody was paying attention to him, but he was still doing this. You know, that's what graduate students are for. So we beat him, but only by 6 months. He discovered cosmic neutrinos too, and I cannot resist showing one of them. This is a muon coming through the Earth, like Markov told us. It has an energy that's yet 10 times higher than the events I just showed you. So this is a discovery, this event by itself is a discovery of cosmic neutrinos. You can't forget all the rest. So now we can also make maps. And so here, I cannot show you a map of our neutrinos because this is a map of 1 year. And because if I showed you 10 years we have, it would all be all blue. This map contains 120 cosmic neutrinos for a background of these annoying atmospheric neutrinos of 138,000. And you see, remember, you expect when you turn on a new way of looking at the sky, you first see the sources of neutrinos that are in the galaxy, in the Milky Way. They're on your nose, right? Nothing. There's absolutely no sign of anything along the direction of the Milky Way. And so what you have to do, so it doesn't look like that at all. So what you do is you only look at these extreme events to not be confused by this background. So you look at the extreme events and what do you see? Nothing. There's absolutely no correlation. So we are somehow looking, these accelerators are more powerful in the universe than the ones that live close to us in our own galaxy. Now, this is a funny thing and is a warning against doing statistics with one event. This was the first event we measured the direction of. And you know, in those days it took a whole day to reconstruct an event of computing. And so I went home very depressed. I said, they all come from the center of the galaxy. So, conclusion, we don't see our own galaxy. We see the whole universe. What you don't see from this, you see a glimpse. You know, I said we expected 10 events, and this 1 year of data had 120. So we actually discovered many more neutrinos than the theorists predicted. So this really on the high side. And I don't have the time to go into this, but the sloppy way to think about it, if you look at this high energy sky, there are as many neutrinos as photons. The energy density in neutrinos in the universe is the same as that in photons. So we'll never solve high energy astrophysics without facing the fact we have to get the information on the neutrinos. So of course this is a great opportunity for a new astronomy. Where do they come from? No clue. So after a few years, by now it's 2016, 3 years we have studied this map, compared it with the map, the position of every astronomical object you can think of, analyze, searching for clusters, nothing. So in the next act of desperation, building a neutrino detector is already an act of desperation. But what we started doing is, and it took some courage, whenever the detectors at the South Pole, I must say the computers, reconstructed a high energy neutrino, we built a system that reconstructed where they came from and sent the information automatically to the astronomy community. So I won't go through this slide, and it doesn't really matter, except to show you that this went to satellite, and you sent what's called an astronomical telegram, and within less than a minute, all the information is out for anyone to look at. And all you get is a message on your phone. But there's nothing really you can do, it's all automatic. And so, this event, we have tried this 10 times. We had no idea whether anyone paid attention to this. And this event was September 17, 2017. It was an event that was interesting. It was almost 300 TV neutrino. Not quite in the category, but most likely. Okay, you could bet on it. There's a cosmic neutrino, but not too much. Here is the picture of the event. It's like the neutrino you saw, but not as spectacular. But probably, likely, cosmic neutrino. So then we found out that in the direction of the event, which we reconstructed to something like 0.2, 0.3 degrees, the Fermi satellite that makes pictures of the sky with high energy gamma rays detected a galaxy, an active galaxy. It's one of these galaxies like ours, but unlike ours, thank God, it's not eating up its own galaxy. This is a supermassive black hole that's rotating and eating up its own galaxy. And not only was this galaxy in the right direction, it was a known galaxy, it was flaring, which means in the last 2 months it had increased its output by a factor 7. And right at its peak, this neutrino came. The probability of this happening by accident is something like 1 in 1,000. Now 1 in 1,000, as a physicist among you know, that's happened. It happens. And, but then someone actually with special type of telescopes I won't describe found out that it not only emitted GeV gamma rays, it emitted gamma rays with 100 to 1,000 times the energy Fermi measured, and that's unusual. So that, the plot thickens now. So MAGIC experiment, they use the atmosphere just like we use ice, and they detect gamma rays instead of neutrinos. So this is in observatory in La Palma. So was anyone looking at this? Because MAGIC and Fermi, we are a club, right? They're all my friends, I know everybody. So then the question was anyone else paying attention? And here is this what I found out. At some point, there were actually more than 20 telescopes looking at this object. And you saw it swift, detected it first. You can see the telegrams, right? There's a web page you can go and look up. And you could see the telegrams come in. Then Fermi here, MAGIC here. And these are mostly optical telescopes. And we didn't realize, we didn't know anything about this galaxy, including how far away it was. And it was so bright that you couldn't see the galaxy. You only saw the high energy radiation from the black hole. And so finally, of course, this is what's called multi-messenger astronomy. So when you produce pions that make neutrinos, then you also produce neutral pions that make gamma rays. So you cannot get the neutrinos without gamma rays, and that's what you are seeing at work here, of combining this data. Then finally someone managed to see the background galaxy, and this galaxy is 4 billion light years away. It's 10 times further than very similar galaxies. So we don't see our own galaxy. Outside the galaxy we don't see nearby sources, so we see something that's 10 times further out. So this must be somehow a special subclass of sources that produces these cosmic rays and neutrinos. But as I said, 1 in 1,000, it's tricky, iffy. So there's something else you can do. This is the story I told you. But IceCube, and so does Fermi, has 10 years of data on tape. On disk now, cheaper. And you can go and look through your old data in that direction of the sky. And we did. And this is what we saw. This is the 10 years of data. Right? So what I've been talking about is this thing. I'm not looking at the right place. This is 2017, this is 2014. And this had 1 neutrino with a bit of low energy stuff. This had more than a dozen neutrinos. No theorist has ever predicted that you could see in a couple of months, which is 100 days, more than 12 dozen neutrinos from the same direction. We actually had enough events on this object that we could measure the spectrum, the energy dependence. This was exactly what you expect from an accelerator. I could go on and on. But this now is, you know, you look at your data in a prescribed way. The chances that this is a fluctuation by accident is 1 in 100,000. So this is real. And so if this is real, given the multi-messenger event showed us to look there, the 1 in 1,000 is probably real too, but it's still 1 in 1,000. So have we solved the cosmic ray problem? Well, look, after more than 100 years, you take anything, right? So we now know 1 source of cosmic rays. And we have found a method to find more, hopefully. And so I won't go into this, I'm going to finish, but if about 10% of the active galaxies in the sky behave like this source, it can accommodate all the neutrinos we see, and it can accommodate all the cosmic rays we see. That doesn't mean this is the answer. We don't know right now. But you know, this is a breakthrough like in a police novel, right? You now know you have the tools to find the killer, but you don't have our hands on it yet. So, on him, or her, or whatever. This was an incredible success, actually. I have to remind you that at some point NSF in the early 2000s decided to gamble their money on IceCube and on LIGO. And they had to wait from the early 2000s till now, but it paid off in a big way. And so multi-messenger astronomy is now, you know, the future. You hear the cash register ring. So let me conclude. I think I've told you everything. It's not worth summarizing, except that, you know, it took a long time for radio astronomy to become an astronomy. When Jansky detected the galactic plane in radio, that paper didn't get a reference for 3 years. I think we're already doing better than that. And but this must become astronomy. You must get, you know, more events, more telescopes, and this is what's hopefully going to happen now. IceCube is building a detector that's on the way to build a detector that's 10 times bigger. They are building a detector in the Mediterranean that is of the scale of the new IceCube, not the present one. And so they are also building a detector in Lake Baikal. So that's you know, we need instrumentation. That's the future of this field. Thank you.
Yeah,
because we may be snowed in by now.
You can't go in.
There are no windows.
We're counting on you, Jonathan.
I can ask one. So beyond just making IceCube bigger, where do you see the future of neutrino astronomy?
No idea. I think the one thing that's clear is you don't want to continue doing this for, you know, you want to put the next step. It's not very efficient to keep playing with too few events. And so I think the future is to build larger and better, not just larger. If you build something 10 times bigger, you will have angular resolutions that are even respectable for an astronomer. So it will be a whole different game with the next generation of detectors. And I predict actually that you will do astronomy with neutrinos without multi-messenger astronomy. That's my prediction, because we are similar to this magic experiment then, both in event rate and in angular resolution. So we should be able to do astronomy. You know, as I say, what you find at this point, you know, it's a long extrapolation saying that active galaxies. The other interesting thing is that, of course, all these models that theorists made, on which we made the guess of building kilometer cube detector, none of them, including this active galaxies, right? Nobody would have predicted that we had to look, you know, 4 billion light years away. And so the whole thing, all the standard ways of calculating neutrino emission are out of the window. As I said, nobody can produce an event that produced 12 neutrinos, 13 actually, and you saw, that's what we saw. But that's good. You know, if I knew what we were going to see, I would do something else.
You
had a question.
Well, I was going to ask, there must be 20 or 40 theories about where these cosmic rays come from.
No.
And we've knocked them out? We've knocked out theories?
Actually, it's so hard to explain the data. When I give a more technical lecture, that's how I introduce. You know, these accelerators not only produce these enormous energy particles. If you look at the luminosity, the energy produced by these accelerators, it's enormous. And so it's very difficult. So there were only, this was one of basically 2 theories. The other theory was that gamma ray bursts, if you know what exploding stars accelerated the cosmic rays. But that we have pretty much ruled out. We don't see neutrinos from this object, and they are much easier to see than these. We have looked at neutrinos from the direction of possibly, or something like 1,500 gamma ray bursts in the history of the experiment. Never seen a neutrino. So there were not that many theories to go by. And so the standard theory for active galaxies, this event, they cannot even produce 1 neutrino in 100 days. So the theory is pretty much out of the window now.
You mentioned improving the angular resolution. When you have a neutrino come in and then it produces your muon, they're not exactly collinear because there's more physics.
Yeah, at your energy they are, but my energy
at your energy they're sufficiently collinear that that's not the...
At the TV, no, if to low, you go to low enough energy, of course.
Sure.
But no, at these energies,
So it's still an
it doesn't.
instrumentation.
Yeah, so if it's much less than 0.1 degree. At a TeV, it's 0.7 degrees or so. It depends how you define the misalignment. But it's of an order of degree at 1 TeV, and then it disappears as the square root of the energy.
Just really curious about the ping pong table room and how you came at this as a, I assume, had you had instrumentation experience before?
No.
And what did it take
But
for
you realize the instrumentation was extremely simple, right? Because I didn't tell you, the Amanda experiment didn't even have any electronics. We just had a photomultiplier and we sent the signals back over a cable and tried to reconstruct it at the surface. So it was, the drilling was by far the biggest challenge. I can talk the rest of the evening about drilling, and you know, we thought you go to Texas and people know how to drill there. No engineering firm wanted to touch this problem. So the drill was designed for everybody who could contribute. You have to realize nobody is trained or has a degree in building IceCube. So you just need smart people who can solve problems. And in fact, the major contribution to this drill, because if you don't do this exactly right, that is provide the heat at exactly the right time in every place, you're going to use 15 plane loads of fuel. We lose less than 1. And solving that mathematics problem, how to supply the heat, was done by a physics graduate student.
Yeah, so my question is to do with, you talked about the purity and the cleanliness of the ice that surrounds the photomultipliers. When you drill the holes and you fill that with the new water and it freezes, does that somehow affect the data that you have after that?
My answer to this question, I've answered this question many times. I said, I wish I had this problem. Because you realize the light you collect travels 425 meters through unperturbed ice, and then for just over half a meter in ice that you have messed up. However, now our reconstructions are so good, so in fact, that it matters. Before it didn't matter because we didn't have enough computing time to reconstruct the events. But now, if we want to reach 0.1 degree, then we have to solve this problem. And in fact, we have TV cameras in the ice, and you know, you put a lot of oxygen, air, in the water when you drill these holes. Where does that oxygen go? And I thought, in fact, we did experiments at Oscar Mayer in the freezers in Madison, and the bubbles collect on the face of the PMT, which is not bad because it collects extra light. But that's not what happens. All the ice becomes totally transparent again, except all the oxygen sits in a thin pipe in the middle of the hole. And so we are now trying to measure the optics of this in detail. So yeah, it has become a problem.
So I guess this is a two-part question. The first, when you saw the really energetic event, then you look back in the data at years prior, and you said it was surprising that you saw an increase in like neutrinos from that direction 3 years prior. So the first question is, why would there be an increase 3 years prior to anyone noticing that something significant was happening? And the second question, which is follow-up, is have you looked at the whole data that you have thus far and looked with angular, and have you seen anything else?
Yeah, so you could see this event in the thesis of a student in the University of Geneva. So we knew about this event. The problem is we had 3 or 4 sources that were equally significant. And what did I mean by that? when you show where someone tells you where to look, and we have a specific way of looking, you look, you know exactly that this is chance fluctuation, it's 1 in 100,000. But if you look in 100,000 places in the sky, it doesn't mean anything. And that was our situation. So this source was already significant, but not something you can claim. In fact, we see our situation is still like that. We see sources like that sticking out. But without the multi-messenger event picking that one out, you don't know which of the 3 other ones are real or a fluctuation. And so the multi-messenger event just lifted this one. You suddenly lose an enormous trial factor. It's just statistics. Yeah. So multi-messenger astronomy took our trial factor away, that's all. It was already there.
Sure. Go ahead. Yeah.
I guess you're saying there's not a lot of theories to explain how or to explain seeing 12 neutrinos all at once. Do you think that I suppose
well,
that? I suppose.
I have one, of course.
I was wondering if you think there's a lot more to be known about neutrinos, or the object of interest 4 billion light years away, or if kind of there's stuff that's unknown.
No, I think the stuff that's unknown, if I understand you, is the astrophysics. That's the other side of the coin, and we have other people here to give much better talk on this. We of course study the neutrinos themselves with the hope of finding new physics, right? This is a particle physics experiment too, as you heard in the introduction. But as far as we know, everything, and we see neutrinos that have more than 1,000 times the energy of any neutrino ever produced at Fermi-Lab. And but they seem to behave very well. And just like, at the LHC, they follow the standard model. Very disappointing.
Yeah. I'm curious how much computing power you guys use to actually do the modeling or the tracking of the articles.
So in this event, which you saw several times, the 5-city block event, there are 300,000. There are 100,000 photons, and we know where every single one is to 2 nanoseconds, which is about like that. And so that's what you fit. But the ice, the transparency is one thing. This ice is made out of about 2 inches layers of snow that have all slightly different optics. And so when you reconstruct this event, you have to propagate these photons each time through these layers of ice. And in fact, this was impossible. Events like the one I showed we couldn't reconstruct until one of our engineers discovered GPUs. And you run the reconstruction on a GPU, you gain a factor of 150 without rewriting the program. It's incredible. And so we are still struggling. GPUs, by the way, are game computers. They do the same thing over and over again. And so, when we propagate 100,000 photons through the ice, each time we refit the event, that's what we are doing. So, unfortunately, it's still difficult to find big clusters of GPUs. They are slowly appearing, but that's what we need.
Yeah. Going back to the drilling holes problem, how did you ensure that the photomultiplier tubes weren't damaged when they were 2 kilometers?
You saw in one of the pictures, they are 2 half spheres of glass, 1 centimeter thick, and they provide the pressure. They resist. Because the hole freezes first at the top. And so there are enormous pressures at the time that the water collapses back to ice. And yeah, we just put them on top of each other.
I was saying at dinner, I worked on an experiment in the Mediterranean where I just thought they were absolutely nuts because they just took two pieces of glass, stuck them together, they put electrical tape around the edge to hold them together so they wouldn't fall apart just during handling, and then they dropped them 2 kilometers into the Mediterranean Sea. But at the bottom is 400 bars of pressure, and it's glass on glass, and that makes a perfect seal. They had a lot of problems, but not for leaks. And I just thought, you must have a gasket, an O-ring, or something.
Of course, we have an under pressure inside.
Yeah, so they also have.
They also must have that, right? Yeah.
There was a question, I said yes.
Are there any promising theories, or do you have any guesses at what kind of events could produce such high energy neutrinos, or just the cosmic neutrinos in general?
Well, you know, the short answer is, we have experts in the audience here, but the short answer is that you need to find somewhere a huge amount of gravitational energy, like a big star that collapses, or supermassive black hole. And so if you convert like 5% of that energy into accelerating particles, you've done the job. And so the idea is that in these outflows or inflows on black holes, you set up shock waves that do this conversion. They don't have to be fantastically efficient, you know, at a few percent level. So shock waves, magnetic reconnection, there are whole textbooks on this, except none of this stuff has made connection to the real world, to the data actually. There's no real evidence for any of this.
In the slides you mentioned that fly's eye particle was like 3 billion TeV.
Yeah.
Do you think your detector can handle that? And if it can, do you expect to ever see one in your lifetime?
Of course, that I have never thought. Yeah, we can. No. I mean, that's what happens is if we saw a neutrino of that energy, it would the size of the ball you saw on the detector display tells you the energy. So that would be much bigger. And but so in the detector, so the whole detector would be filled with light. But it would detect it. No problem. It's just that the ball is bigger, so it compensates. It's not like if you put that same energy in the same volume, yeah. Now our photomultiplier, if you have a big event, at the very beginning when a neutrino interacts, makes a nuclear reaction, where the nuclear reaction is happening, some of the photomultipliers are saturated. They cannot count the number of photons anymore.
I just wondered, are you involved in other experiments being developed right now? Like, I think this talks about one in Victoria, BC, of them potentially putting in strings in the water. Are you involved in any other experiments advising them?
Yeah. So I should have mentioned that one. They really haven't done, they have been doing tests. In fact, they're my collaborators, right? They're all, I think they're all IceCube people, right?
That's right.
Yeah. And
faculty here.
so the problem with the experiments in water, they have solved all the problems that we solved with the Amanda detector. So they can build a big detector. Their problem has been to build the infrastructure on the bottom of the ocean. And Canada has developed such an infrastructure which is just can be used, I understand. I'm not involved, but so the idea is to test out this facility. It's off Vancouver somewhere, right? Is to test this facility to see if you can deploy strings and support strings. Yeah, that's, you know, having experts that solve your main problem already, I mean, that's a big step forward. So they have deployed things. I've seen data of modules that don't detect neutrinos, but that measure the water and test whether this facility can be used. So who knows? Yeah.
Just have a question from the online audience. What are you now learning from the atmospheric events that have been detected?
Not much. Yeah. Well, in fact, it's part of the answer to the fact that the neutrino seems to behave. We measure neutrino oscillations. We measure the mass of neutrinos and their mixing parameters, just like snow and other and super K and so. But we measure their properties at 10 times higher energy. Our sample of neutrinos we use to measure the mass is 10 times higher energy than what they use at Fermilab, super K. And so the hope is that you find some differences so that you discover new physics. And up to now, we just find all the same results that other experiments have found since '98, right? And on the other hand, we're still working on this too. I never believed we could do neutrino oscillations with this experiment. But there was a bright graduate student in Berlin who's now a professor in Alberta who solved the problem. I couldn't believe it. And so now we are developing this technique.
Like the McDonald Institute faculty.
Yes.
Okay, I don't see any other questions, so let's thank Dr. Halzen again for